As I alluded to in the last video, molecular orbital theory is necessary in order to be able to understand UV-Vis spectra of organic molecules. Now, molecular orbital theory is one of those topics that most chemistry students find quite difficult to understand. And I'm going to begin this whole discussion by saying we're only going to use MO theory at the level that we needed to use it in order to explain the spectra of conjugated organic molecules. So molecular orbital theory is a higher level theory of bonding than valence bond theory. So as you recall, valence bond theory involves hybridization of orbitals to form, sp2 and sp3 hybrids, followed by the overlap of those hybrid orbitals to form bonds. But there are certain phenomena that cannot be adequately explained using valence bond theory, and when we come up with some of those phenomena, such as what I introduced you to in the last video, the UV-Vis spectra of conjugated alkenes, the bond lengths, etc., then we need to go to a higher level theory. Okay, so I'm going to give you now some basic principles of MO theory. I am assuming for the purpose of this video that MO theory is at least something that you have seen in a general chemistry class. So the first principle of MO theory is that atomic orbitals on atoms in a molecule, on all of the atoms in the molecule, are combined to give the same number of molecular orbitals. Now, if you're doing an absolutely pure MO approach, you take all of the orbitals, all of the atomic orbitals on all of the atoms and combine them. Nobody actually does that. What most people care about is all of the valence orbitals. So that's what they will call their basis set, and the number of molecular orbitals you get out has to be the same number of atomic orbitals that you put into your basis set. We're going to get even less rigorous than that, and we're actually going to, as you're going to see in our treatment, mix valence bond theory with molecular orbital theory. Okay, so when you get these molecular orbitals out of the atomic orbitals, some of the molecular orbitals are lower in energy than the atomic orbitals from which they were created. And these are called bonding molecular orbitals because the formation of a chemical bond is an energetically favorable process. Now, similarly, some molecular orbitals that you get out are going to be higher in energy than the atomic orbitals from which they were created, and these are going to be called anti-bonding molecular orbitals. So anytime you take two atomic orbitals and combine them to give molecular orbitals, one will be a bonding MO and the other will be an anti-bonding MO. The reason you need to do this is that the total energy of the system has to be conserved. So if you're going to have one orbital that's lower in energy than atomic orbitals, you're going to have another orbital that is higher in energy than the atomic orbitals by the same amount. Just simply coming up with a theory of bonding cannot change the overall energy of the system. So molecular orbitals are orbitals, and just like atomic orbitals, the capacity of a molecular orbital is 2 electrons. You got to remember that. No matter how big a molecular orbital may look like in space, it still cannot hold more than 2 electrons. So each filled bonding molecular orbital represents a chemical bond. And electrons in anti-bonding molecular orbitals will reduce the number of bonds, but we actually will not need to ever use this fact because it's not going to be true for any of the molecules that we're going to look at in this course. Finally, this is what students may have the most trouble with. Molecular orbitals are delocalized over the entire molecule. So a bonding MO does not simply represent a bond between 2 specific atoms. We like to draw structures where we put bonds between specific atoms, but molecular orbital theory is a theory of delocalized bonding rather than localized bonding. Okay, so as I alluded to, we will adopt a simplified MO treatment for conjugated alkenes in that we will only use MO theory to explain the pi bonding. The sigma bonding will be explained by the overlap of sp2 hybrid orbitals on each carbon using the traditional approach of valence bond theory that we've used all along. So before I get to a conjugated alkene, I want to actually start with the simpler case of ethylene. So ethylene has 2 carbons, each of which has an unhybridized p orbital. Okay, so if we assume sp2 hybridization for ethylene, there's an unhybridized p orbital left over on each carbon that's not part of the hybridization. So those orbitals can combine in phase, and what I mean by that is if you look at the diagram on the right of your screen here, you have the blue lobe overlapping with the blue on one carbon atom overlapping with the blue lobe on the other carbon atom. So this in-phase combination gives a bonding molecular orbital, and the out-of-phase combination where the blue is next to the red so they cannot overlap or combine constructively to form a bond, that is then an anti-bonding molecular orbital. The dashed line going up and down between the 2 orbitals is called a node, and by definition there is 0 electron density at the node. The fact that there's 0 electron density at the midpoint between the 2 carbon atoms is suggesting that if this orbital should be occupied, there will not be any bonding happening as a result of electrons going into that orbital. So the anti-bonding orbital is higher in energy, and then the other terms that are on this diagram is psi1 and psi2. So psi is the Greek letter that we use to give to label molecular orbitals with. The psi1 is going to be the lowest energy, and then psi n, whatever n is going to be the highest energy molecular orbital. In this case, there are only 2 molecular orbitals. The bonding one is occupied, so it is called the HOMO, standing for highest occupied molecular orbital. The anti-bonding orbital is unoccupied, so it is the lowest unoccupied molecular orbital. Okay, so why do we have the HOMO occupied? Well, each carbon uses 3 of its 4 valence electrons to form the sigma bonds. So you have the sigma bond to the other carbon and the sigma bond to each of the 2 hydrogens. So what that means is there are a total of 2 valence electrons left over to use for pi bonding. Okay, so those 2 electrons are going to go into the lowest energy orbital. Just like in the Aufbau principle for atoms, you want to put electrons into as low an energy orbital as you possibly can. Therefore, it is going to be filled. So since there is 1 filled bonding molecular orbital, there is 1 pi bond, which is what we would expect for ethylene from valence bond theory. So relating this back to spectroscopy, moving a molecule from the ground state to the excited state involves moving an electron from the HOMO to the LUMO. Okay, so now let's consider 1,3-butadiene, which is the simplest conjugated alkene. So in this case, because there are 4 carbon atoms, there are going to be 4 unhybridized p orbitals left over, which will combine to give 4 pi molecular orbitals. So there are 4 different possible combinations of the 4 p orbitals, ranging from completely in phase, as you can see on the bottom, to completely out of phase. So in this case, the lowest energy molecular orbital, psi1, has 0 nodes. The second one, psi2, has 1 node between the 2 central atoms. Psi3 has 2 nodes, and psi4 has 3 nodes. So notice that psi1 is bonding between C2 and C3, and since this orbital is filled, that actually explains the partial pi bond between the 2 central carbons. So the HOMO in this case is psi2, because we have 4 electrons that we have to put into this pi system, and since the maximum capacity of an orbital is 2 electrons, we have to fill 2 of the orbitals to be able to put the 4 electrons in. So promoting the molecule from the ground state to an excited state would involve moving an electron from the HOMO, which is psi2, to the LUMO, which is psi3. And the energy required to promote an electron from the HOMO to the LUMO can be in the form of light. So the energy difference between these molecular orbitals corresponds to light with a wavelength of 217 nanometers. If you recall that the UV region of the spectrum is from 200 to 400 nanometers, that is why this molecule absorbs light in the ultraviolet region of the spectrum. Okay, so that's the basic of molecular orbital theory that you would need to understand UV-Vis spectroscopy and why certain organic molecules can absorb in the ultraviolet. In our next lesson, we will look more specifically about what a UV-Vis spectrum looks like and the important features that you need to get out of it.